Hey, everyone. Hey, everyone. My name is Joey. Blind Sight is our project to build a visual prosthesis to help the blind see again. Users would wear a pair of glasses with an embedded camera and receive an implant in their visual cortex. Scenes from the environment are recorded by the camera and processed into patterns of stimulation delivered to the brain, causing visual perception and restoring functionality. Now, Blind Sight will be enabled by placing our implant into visual cortex. This is a new brain area for us, and this brings new opportunities and challenges. So the surface of the brain for visual cortex represents just a few degrees of angle in the center of the visual field. Larger fields of view are represented deep within the cortical folds of the calcarine fissure. Our threads are able to access these deeper structures, providing the possibility of restoring vision over a functionally useful visual field. So the N1 implant has had experimental stimulation capabilities for quite some time, but our new S2 chip is designed from the ground up for stimulation. It provides over 1,600 channels of electrical stimulation, high dynamic range recording capabilities, and a wide range of microstimulation currents and voltages. We can achieve these capabilities because we are vertically integrated and we designed this custom ASIC in-house. Similarly, we design and fabricate our electrode threads in-house. And here you can see one of our standard threads designed for recording in an electron micrograph. For Blind Sight, our requirements are a little different, and our vertical integration allows us to rapidly iterate on the design and manufacturing of these threads for this new purpose. So here, I'm using red arrows to highlight the electrode contacts, which are optimized for stimulation. And as you can see, they're a little bit larger, which results in a lower electrical impedance for safe and effective charge delivery, which is important for Blind Sight. Now, how can we calibrate our implant for Blind Sight? So here's one way. We stimulate on the array, picking, say, 3 different channels. The user perceives something, say 3 spots of light, somewhere in their visual field, and points at them. We track their arm and eye movements and repeat this process for each of the channels on the array. And here's what a simulated example of a Blind Sight vision could look like after calibration. Now, I showed you how for Blind Sight we need to insert threads deeper into the brain than we have previously. And doing this requires state-of-the-art medical imaging. So we worked with Siemens to get some of the best scanners on Earth. We built out our imaging core from scratch in the past year. Actually, it was faster than that. It was about 4 months from dirt to done. Since bringing the scanners online, we've scanned over 50 internal participants, building out a database of human structural and functional anatomy. What can we do with the imaging information from these scanners? So medical imaging can be used for surgical placement. It lets us parcelate out brain regions by their function. And we use our imaging capabilities to refine the placement for telepathy. It also gives us the capability to target new brain regions for future products, such as Blind Sight or our speech prosthesis. And we're working towards more capabilities. So one-click automated planning of surgery from functional images to robot insertion targets. Here you can see a screen capture from one of our in-house tooling to do end-to-end surgical planning. You can see a region of motor cortex known as hand knob and the thread trajectory plans that'll be sent directly to the robot. This is a really incredible degree of automation that's only possible because we're controlling the system from one end to the other.